Okay, let's look at a couple of additional reactions and tie up this whole theme. We're going to look at reactions at the alpha position, but now instead of being for ketones and aldehydes, we're going to look at esters, carboxylic acids, and the derivatives. Okay, one of the things that we might want to do is take a carboxylic acid. Carboxylic acids are fairly easy to get hold of. There's some of them in nature. And make a synthetic protein, I mean a completely invented one. Proteins are made up of small monomeric building blocks that are alpha amino acids. So if I have an R group, and then I have, here's the carboxylic acid, and here is my alpha position right here. What if I could somehow like this? That's your alpha amino acid right there. That's the building block of proteins. We can't quite do that in one step because this is a base, got a little pair of electrons, and that's an acid. And when I think about pKa's here, pKa of this position is about 15, and the pKa here is about 4.5 going on to 5. They're usually about 4.8, so let's say 4.5. So how much more acidic is this place than that place? Like 100 million. I mean, if you're going to say, if that's 15 and that's 5, let's round it up. Every single different in digits is a factor of 10. So, there's 6. Yeah, it's 10 billion times more reactive here than it is there. So what I'm hoping to do is build a leaving group into here. If I'm going to put a bromine here, now I could really do some reactions. So that's what our strategy is. So this is right here. So we can't put this molecule in base hoping to take that alpha hydrogen and therefore build a leaving group into it, because the other position is 10 billion times more reactive than it. Okay, here's how we're going to get around that. Mr. Volhardt and Zelinskii put their minds together and came up with a strategy. And the strategy is not unlike the Williamson strategy of, I'm going to just take something off the table. First thing that we're going to do is, so ultimately this is going to be a bromination. But I'm going to make the acyl chloride. It's cleaner, just on paper, if we make the acyl bromide, because now everything's a bromo and you don't have to worry about having chloros and bromos in the molecule at the same time. So there's no particular reason to use PBr3 other than PCl3, other than it's slightly prettier to look at. Okay. Made the acyl halide, and now this is now the most acidic position. Chances are we only want to substitute one time at that alpha position. If I put this in base and then let some halogen take a look at it, I would perhalogenate both of those positions. So this is one of those cases where I want to do the monohalogenation. So I would do this in a tiny amount of acid. There is some evidence that suggests in this particular case you don't actually really need the acid. So previously when we saw the monohalogenation, we saw a little bit of acid and the halogen itself. Go ahead and continue doing that. I'm just telling you that this reaction is easy, and I'm told that you don't need the acid. If you write it in, it's still correct. So I'm going to do the monohalogenation. Now let's get rid of the acid. Let's get rid of the acyl bromide and convert that back to being an acid. How would we do that? Two possible ways. You could add hydroxide, and hydroxide would do the nucleophilic acyl substitution here, but hydroxide is still a base, and that's still acidic right here. So I probably wouldn't put it in base. I'd just do the acid catalyzed hydrolysis of this acyl chloride, acyl bromide. So this would be H plus and H2O, and you just do the hydrolysis, which is probably one of the reasons why, although a small amount of catalytic acid would help my bromination step to occur, I got to make sure that there's no, that there's not a great deal of water here. So if I'm catalyzing this step with acid, I'm adding a single drop of concentrated acid to do it. I'm not adding dilute acid in any way at all, because I want to keep the water out, because water will make this. Okay? So this is, what have we got? This is really a nucleophilic acyl substitution. This is monoalpha monohalogenation. This is hydrolysis. Okay. Now I have a real leaving group. And with that leaving group in there, I can plan my next reaction. You can do this with esters as well. It's not as complicated with esters, but it's still complicated. So here is ethyl acetate or ethyl ethanoate. You name this substituent as the alkyl substituent, and then you name this as the carboxylic acid derivative. So that molecule right there has alpha hydrogens. Because we've written it in the stick form, we don't get to see them. Okay, let's try and remove those. If I did this again, I would need catalytic amounts of concentrated acid. I would be able to monohalogenate at that position. Okay. What if I tried that in base? What if I tried to do lots of brominations and put this in base? Take off. Nope. That's also a nucleophile. Just because somebody tells you, hey, I've put it in base, doesn't mean that you should take their word for it. It says it's a base, but it's also a nucleophile. Okay, we're going to do the nucleophilic acyl substitution. So you've got to be careful what you do with the esters, of exactly what base to put them in. This is absolutely key. So the trick with esters ester reactions have to use exactly the correct base. If you don't, it goes wrong. Okay. That is ethyl ethanoate or ethyl acetate up there. If I wanted to grab hold of the acidic hydrogens on the alpha positions, there is only one base that I can use. What would that base be? Here's a clue. This is a phenyl group and an ethyl group. Okay. If I put that into solution, with an ester that is kind of its mirror image. This is a benzyl and that's a phenyl, so that's, you know, I can't make the ketone B directly on the ring because that would be too many bonds. I put those both in solution together. They scramble. they will trade places with one another. I put 2 things in, I'm going to get 4 things out. They're all esters. I'm going to get my 2 original ones plus I'm going to make this, and I'm going to make some of that. They scramble in a reaction that's called transesterification. Here's why. In an ester, your alkoxide is the leaving group. And all of those leaving groups, because they're all based on alcohols, they all have the same pKa. They all have the same basicity. They all have the same ability to grab hold of a carbon and make a bond. Asterisk. What is the asterisk for? Except phenol and phenol's alkoxide ion, which is called phenoxide. Phenol, remember, is 1,000,000 times more acidic. That is 1,000,000 times less basic than most alcohols. That means it does not hold on as well as the others do. It's a better leaving group. So this turns out right here. This is a better leaving group. Now, you put 2 esters together, or you put an ester and an alcohol together, they are going to scramble and interconvert. And when it pops off, the leaving group is a base. So, my original question is, ester reactions must use exactly the correct base. Here is ethyl ethanoate. If I want to gain access to the alpha position by putting this in a base and having the base remove one of those alpha hydrogens, what's the base that I have to use? Whatever the leaving group is. For esters, the base has to be tailored to the reaction to be exactly the same as the leaving group. Now that's a new difficulty that we have to face, but it's also something that's really simple because we're going to get into the habit of writing the base immediately underneath the leaving group. So the base is going to be the same as the leaving group. Okay, let's make an alpha nucleophile from an ester. Here you go. ethanoate still. The base that I'm going to use, what's the name of the base? It's going to be this, those two with a negative charge on the oxygen. 2 carbons. That's ethoxide. 2 carbons, negative charge on an oxygen. All right, let's go take it. That's the most acidic position in the molecule. This is a base. It's the same as the leaving group. So it can do the nucleophilic acyl substitution to its heart's content. Ethoxides don't have hearts. It could go boom, open this up, close that down, kick this off. What have they achieved? Nothing at all. So that nucleophilic acyl substitution can just churn because the product is the same as the reactant. That's the whole point. I'm not telling you it doesn't happen, I'm saying it is of no consequence anymore. Okay, what else have I got? Oh, I've got an acidic hydrogen. Oh, that's great, I'm also a base. You've previously only seen me as a nucleophile. I can also be a base. Let's go take it. We should write this as an enolate, because that's the most correct way. Let's just localize that as a nucleophile, because we're going to make some big, ugly molecules today. And localizing that negative charge is going to make our life a little bit easier. Made ethanol, and I've made a carbanion nucleophile, which is really an enolate. It's in hybridization, it's in resonance with the molecule of the enolate. All right, what's it going to react with? Another molecule of itself. Here it goes. There's the nucleophile. There's the electrophile. It's going to be a nucleophilic acyl substitution. We've seen these before. They were nice and small when we did them before. They're going to get a bit bigger. All right, so now I've got all of this fragment and all of this fragment. Just keep one of them where it is. That's my carbon. The carbonyl opened out to be an alkoxide. On this side, I've got a methyl. On this side, I've got an ethoxy group. And I now, because I localized that carbanion, instead of being an enolate, I now know which carbon it's attached to. It's attached to this carbon right here, which is a CH2. Which is then attached to that carbonyl, which is then attached to another ethoxy group. Okay. Nucleophilic acyl substitution. The nucleophile comes in, the pi bond opens. When the pi bond reforms, it kicks off the leaving group. We've seen it, we did it, it wasn't difficult. It's the same thing, it's just bigger. So when that reforms, I'm not going to break a carbon-carbon bond. I'm going to break a carbon-carbon bond, I'm going to break the alkoxide. I'm going to break that one. Okay, so this is all going to go sp2 now. So here's my methyl, It's attached to the carbon, which is now back to being an sp2. So if I write it as the trigonal plane that it is, right, then I get a CH2 here, and then it goes up to another sp2 carbon. And it doesn't look so frightening anymore. Your product will have an undulation in it, and your product will always be the same thing. I've got a ketone and an ester in this molecule. Is this an ester ketone or a ketoester? Which one of those two groups is the most important? The one with the most bonds to oxygen. The ester has 3 bonds to oxygen. The ketone only has 2. So that's carbon number 1. The functional group with the most stuff going on gets to be the most important. So this is a ketoester. There's my ester, it's carbon number 1. That's the alpha position. This is the beta position. There's alpha and the beta. This is a beta keto ester. The product of a Claisen is always a beta keto ester. Okay? That's as easy as they get. They don't get easier than that. It's always the same thing. Let's do it a couple of different times. Base you use has to be the same as the base in the ester. If it's not, you're gonna scramble your leaving groups. You're gonna get more products than you were anticipating, which is never a pleasant surprise. Okay, let's do it again. So we've seen before, we did an aldol. 2 molecules of the same thing. An aldol is 2 aldehydes. You put it in base, you make a nucleophile out of one of them. That nucleophile reaches out and treats the other molecule of aldehyde as a reactant, as an electrophile. And then you move on. You always make the same product. Same thing's going to happen here in the Claisen. We take an ester, we convert one of them into the nucleophile. That nucleophile treats the other molecule of ester as an electrophile. 2 esters make a beta keto ester. The next thing that we saw with the aldol is take 2 different aldehydes or 2 different ketones and mix them together. And you get a mess, because you've got alpha hydrogens everywhere, and you can make the nucleophile everywhere, and probably try and make the best enolate, but you're gonna get a mess. Same thing with the Claisen. Same strategy to avoid the mess. Limit the number of alpha hydrogens. So we have a mixed aldol and what we call a cross Claisen. Cross Claisen is the same as saying mixed Claisen. Okay. The key here is limit the number of alpha hydrogens. Now, Claisens have an advantage over aldols that's twofold. One, they have a leaving group. So the reactions turn out a little bit cleaner. You've got less atoms in your product than you do in an aldol. Plus, one side of the carbonyl is taken up with the leaving group. So I only have alpha hydrogens on one side of the molecule. So if I want to take 2 different esters, I can really work to limit the number of alpha hydrogens in this molecule, in this reaction. So if I did this, both leaving groups have to be the same. If they're not the same as each other, all bets are off. Okay, I am not starting this reaction if both of these leaving groups are different. Because that's a phenyl. I don't have any alpha hydrogens right here, which means this reactant is now primed to be my electrophile. Right there on that carbon. I have 2 alpha hydrogens right there. Which means if I put this in base, and the base that I'm going to use is the same as my leaving group, here is where my nucleophile is going to be generated. Right there. Okay, let's do it. Step 1. I'm going to write this out so that you can see the hydrogens. Write the base underneath the leaving group of the ester. Have it reach out and grab hold of that hydrogen. That hydrogen is going to dump its electrons. And now I have there's my nucleophile. Have the nucleophile reach out and grab the carbonyl. It's this step right here, same thing. Okay. Write this out. So that's the carbon that's being attacked. The pi bond is broken and has left me an alkoxide. On the right, I have an ethoxy group. On the left, I have a phenyl group. Then I'm attached to this carbon. That carbon is a CH, and it's attached to 2 separate things. Attached to a methyl, which I'm just going to write here to get it out of the way. It's attached to that methyl. This is the CH. It's attached to that methyl. And then it's also attached to this carbonyl, which is the rest of my ester. Have the carbonyl reform and kick off the leaving group. There's my phenyl. Here's my reformed carbonyl. This leaving group is now gone. It is attached to a CH, which is attached to a methyl, and also attached to another carbonyl, which is part of the ester that remains intact during the reaction. I lose a molecule of ethoxy at the end, and I pick up got to account for a molecule of ethanol here. Okay? That is a beta keto ester. If it's not a beta keto ester, you've got the wrong number of carbons in your chain somewhere. You've attached the wrong thing to the wrong place. go backtrack. Okay, so we're going to do everything to the Claisen, which is actually a little bit easier than the aldol. We're going to do everything to the Claisen that we did with the aldol. Show you one that's nice and simple. Have the two fragments come together. Show you two different ketones or aldehydes. Make those come together with a choice or a strategy. Limit the number of alpha hydrogens. And then what did we do with the aldol as the big finale? Intramolecular. Same molecule. And the intramolecular aldol only worked if? If you can make a 5-membered ring or a 6-membered ring, the reaction will work. If you cannot make a 5-membered ring or a 6-membered ring, it will not work intramolecularly, it will still work intermolecularly. So the intramolecular Claisen goes by another name. It's called a Dieckman. And a Dieckman is going to be, we're going to want our esters to be a specific distance away from each other. So here's an ester. Now with an aldol, we had alpha positions, because we had a ketone, we had alpha positions on the inside and outside. For a Dieckman, you're only gonna have the positions on the inside. Because at this end, you're going to have another ester at that end. The esters are going to be terminal. So I need, right, so one of them I'm going to generate a nucleophile. The nucleophile will be at the alpha position. I'm going to need 5 or 6 spaces to get to the electrophile. So look at your molecule. Here's the alpha position to the left-handed ester right here. That alpha position is going to end up being my nucleophile. This carbonyl carbon is going to end up being my electrophile. I need the number of carbons in that part of the chain to either equal 5 or 6. That's the only way that this reaction will work. So if this is 1, 2, 3, I might do this wrong, 4, 5, 6, this will work. So that is a 1, 2, 3, 4, 5, 6, 7 carbon chain. But I make the nucleophile 1 carbon in. So this is a 1,7 diester. It is going to make a 6-membered ring. If it is a 1,6 diester, it will make a 5-membered ring. I'll show you what a 1,6 looks like. 1,6 is, because we're going to write them in zigzag form because it's just easier. 1,6 goes . 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, 6 carbons total in the chain. That's an alpha position right here. So I'm going to build my nucleophile there, and then it will reach out and build a new bond here. There'll be 1, 2, 3, 4, 5 atoms in that ring. Okay, let's do the mechanism. There's a carbon here. The base of my choice is whatever this molecule dictates to me. Whatever that alkyl chain is, that's the base that I'm stuck with. Take the hydrogen, dump those electrons. It's really an enolate, but there's never a better time to show the shorthand. You localize the charge on that carbon. It's easier to follow. Electrophile is attacked by the nucleophile. Here's where you put your finger on the page and you figure out what you've got. Or, something that we didn't do the other day, is you can number the positions. One, two, three, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. The carbon that was under attack. Number 7. Number 7 is holding on to the alkoxy group that's going to be our leaving group. 7. Let me see which way I'm going to do this. Is attached to 6, which is attached to 5, which is attached to 4, which is attached to 3, which is attached to 2, and 2 is attached to 7. 6, 5, 4, 3, 2. I've made a new bond from carbon 2 to carbon 7. That's the new bond between carbon 2 and carbon 7. Carbon 2 is also holding on to the ester group from carbon number 1. And the difficult part has been done. Let's just complete your nucleophilic acyl substitution. Kick off that leaving group by reforming your carbonyl, and there's my beta keto ester. It's just part of the ring now. So I have to account for a molecule of alcohol that I generate in this step, and I have to account for the loss of an alkoxide in the last step. Okay? And with that, we're done. So all the difficult chemistry that is ketones and aldehydes and carboxylic acids that then just progressively snowballs and becomes bifunctional molecules ends here. Friday we will start biomolecules, which essentially for us is going to be sugars. The amino acids that we'll teach you in organic chemistry is trivial in comparison with what you'll learn in biochemistry, but we'll do some real chemistry of the sugars. Okay, quiz, Friday. Yes, this? Sure. I'm not seeing so many smiling faces today. This is actually easier than the aldol. 1, 2, 3 arrows. It's always the same thing. You have a predictable product. Quiz Friday on the Claisen condensation.